Alright, let's quickly cover conductor loss. So from the general, so you learn that DC resistance. So I'll start from DC resistance. So if we have this structure, we have L, radius R, and then conductivity here, right? So RDC, L divided by A, right? So sigma L divided by pi R square, right? So for this case, DC current flows across the entire cross section of wire, right? So this is easy compared to the DC RF resistance. So RF current flows close to the surface of the wire, right? So we know that when this electric field become 1 over E, at that time G, right, is 1 over R, but this is skin depth, right? So the distance which make electric field is 1 over E of initial value, right? So this is skin depth. So you know skin depth 1 over pi frequency mu sigma conductor, right? So for this case, RF resistance can be resistance of this is 2 pi R, and the thickness become skin depth, right? Because the current is mostly flowing to the surface of the wire in RF frequency, right? So RF 1 over sigma L divided by 2 pi R sigma skin depth, right? This is the area. So we have this. So mostly RF increases, right? So as frequency goes up, skin depth is reduced. So RF increase more, right? So that's why as the frequency goes up, the loss in the circuit is higher. So we need to design some amplifier to compensate that loss, right? So that's kind of hardware design, circuit design is more difficult in high frequency. So sheet resistance. So if you see some spec of PCB, and then PCB has some conductor. So to characterize that conductor, we use sheet resistance. So this is skin depth. This resistance is 1 over sigma, and then if the current is flowing this way, right? So this is length W skin depth, right? So if if we put L and W and L is same, then 1 over sigma n is skin depth, right? So we define this as RS, so the sheet resistance ohm, right? So this is sigma is Siemens per meter, so this become ohm meter, right? And then this is skin depth is just meters, so this become ohm, right? So this is ohm per meter square. So in a square, right? So because I said L and W are same, so sheet resistance means the resistance of one square, right? So let's say if we have some PCB conductor, and then they said in spec they said 10 ohm sheet resistance, right? They just define ohm, but you just understand as length and width are same. So if we use that material and then connect this way, right? Then how resistance? 20 ohm. If you connect, so this is same, right? If we put 3, so current is flowing this way. So this is 30 ohm, right? So if we know the sheet resistance, right? Any structure, if we have any structure, then we will know that resistance, right? So if we have this, let's say this is square, another one, so this is also 20 ohm. This is square, 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 square. This is also 20 ohm, right? So this is 10 ohm. This is also 10 ohm, right? Because this width and length are same. So from this sheet resistance, right, then we can know any size of this kind of conductor plate. So if you plug this one, you know this equation, right? So then R become omega mu divided by 2 sigma n square root of it, right? So this is the resistance, same sheet resistance. And then conductor loss of in microstrip. So if we have this width and signal, if we have a conductor as a signal line on the microstrip line, this is epsilon, this is ground. So conductor basically current will flow at the surface of this conductor, right? So R C is defined as RS. We use surface resistance of the conductor and then divide by characteristic impedance of this transmission line and divide by W. So this RS is sheet resistance. Right, so if we increase the G0, then C can be reduced. So if we use RS, less RS, right, alpha C, attenuation from the conductor loss will be smaller, right? So this is attenuation due to conductor loss. Right, so okay, so let's wrap up about this conductor loss.